Good. All right. You have to introduce yourself again.
Yeah,
It's the
so
first time.
great. I'm Pete Shadbolt. I'm a co-founder of PsiQuantum. I've worked on quantum computing my whole adult life. And yeah, I'm here in Silicon Valley building a machine.
Building a big machine.
Yep.
Yeah. I've covered quantum computing for a long time. I'm left still with lots of questions. It's a difficult thing to explain. If you had to take a crack at it, how do you try to explain it to someone at a dinner party?
Yeah, so at a dinner party, so first of all, I mean, it is a pretty involved topic and it's been poorly communicated, in my opinion, over and over again. The way I describe it at a dinner party is to start with a quote from Rolf Landauer, information theorist at IBM for a long time. Rolf Landauer said, information is physical. It's a pretty profound thing, actually, in my opinion. When I think about information like a sound or a number or a word, I don't know about you, but I think about an abstract thing that's floating above my head.
Yeah, 100%.
What Rolf is saying is that that's not the case. Information only exists when it's encoded in something, in action potentials in our brain, ink on a page, electrons in our computer, rocks on a beach, whatever. It's a physical encoding. And all of the computers that we have ever used to date have run on the physics of 100 plus years ago of Maxwell and Newton. The basic idea of quantum computing is that we are going to build a machine that uses the new physics, that uses quantum physics. And the way that I think about that is if information is physical, if the things that we can do with information are dictated by the physics of that encoding, by introducing new physics, by building a machine that computes using quantum physics, single atoms, single electrons, photons, whatever, we're introducing new operations that we can do with information. And this is like you're playing a game of chess with somebody. There's some established set of rules. They introduce some new rules. Now they can run new strategies, new moves in the game, and you're going to get absolutely destroyed in that game of chess. And that's really been the principle that we're going after with quantum computing. We're going to use new physics. We're going to unlock new operations and thereby new algorithms that for some applications are just like devastatingly powerful relative to the classical algorithms that we can run on regular computers.
So you get these new tools, this new structure, new
Yeah.
questions you can ask.
Yeah.
Traditional chips, since semiconductors were invented, we've always talked about bits of
Yep.
information,
Yep.
this idea of transistors that are like switches that flip between 1 and 0. In quantum land, this central construct is called the qubit.
Yeah.
What is a qubit and how does it differ from a bit?
Yeah. So in quantum physics, we have ideas of superposition and entanglement. These are words that we've come up with to describe physics that humans hadn't observed up until about 100 years ago. And we had to come up with new language because it's actually very hard to describe these things by analogy. And the double slit experiment is probably the most famous piece of quantum physics. So you send an electron or a photon at a wall with two holes in it.
Uh-oh.
Oh, did they cut power?
No, our light died. We're back. Thanks, guys.
Cheers, guys.
Oh yeah, everything's good. Okay, well, let's go back to qubits. So bit is the fundamental unit and thing everybody knows for traditional semiconductors, the 1 and 0, the on and off.
Yeah.
In quantum land, everything revolves around a qubit. Can you describe a bit of what a qubit is and its properties?
Yeah, so if you want to run these quantum algorithms, if you want to unlock the promise of quantum computing, you need to encode information in a quantum thing. That means an atom, an electron, a photon, something that can be in a quantum superposition state and that can be entangled. And the qubit is the sort of abstract description of the unit of information that from which the whole quantum computer is built. And in physics, we say it's a two-level system, which just means it's something that can have two different states and is quantum mechanical.
Yeah.
So people use energy levels of an atom, for instance. They'll use energy levels in a little superconducting device. There are people who use things in diamond and all sorts of different microscopic, usually pretty exotic devices. What we do is we use a single photon, so a particle of light. And what we just really done, we basically just put the photon in one place or the other place. So it's really quite like the double slit experiment, if you're familiar. Like you basically are just giving the photon the opportunity to be in one place or the other place. And then it goes into a quantum superposition of being in both places at once. And that's kind of the foundation for our qubit. Yeah.
And there's parts of this that are difficult to explain. There's lots of parts of this that are difficult to explain, but in the big picture, we have room-sized computers. We have building-sized computers that can do fantastic things. They can crunch away on these more traditional problems. The promise of quantum computing is just that we can ask a whole different set of questions because it allows us to tap into this different set of rules. Like, what is the class of questions for people to wrap their head around that this opens up for us?
Yeah, so just, I mean, firstly, like, you're right, it's hard to describe. And that difficulty of describing quantum computing is rooted in the difficulty of describing quantum physics. There's two pieces of comforting news on that. The first is that the mathematics is the most accurate math, the most accurate physical theory humans have ever come up with. Stood the test of time for 100 years, and it fits on a postcard. It's like high school arithmetic, the basic mathematics of quantum physics. Totally uncontroversial, really pretty straightforward to deploy. And then secondly, like, people always say, oh, the qubit is so hard to understand and mysterious, and they write these huge long articles trying to make sense of it. If you think about regular computers, and you've been working, of course, on these things for too long. I was thinking, like, go to a tech conference and get your hundreds of technology experts and say, hey, can you get on the whiteboard and tell me how a transistor works? Like, talk me through Fermi levels and electron hole pairs and so on. And it's like, no chance, right? Like, I've got a PhD in physics. Today I would struggle to describe to you how a transistor works. I've forgotten most of that stuff. It's pretty involved physics. So, like, the fact that the foundation of the technology is a little tough to comprehend is not actually unusual in that sense. And then as far as the application space, we're not coming for Excel. This isn't a general purpose computer where we're going to just speed up all of the things that we do today with regular computers. This is a supercomputer. It is a high performance computer, and it's targeted at a limited set of, we believe, extremely lucrative applications. And so...
Sorry.
Yeah, no, you're good. So it's not about an incremental, like, 2x speed up. It's really about going for problems that are effectively impossible using conventional supercomputers or indeed AI. And where do those problems lie is an important question. If you think about Fortune 100, I don't know what you visualize when I say Fortune 100.
I think about, well, I don't know. I would think about energy, finance, medicine, chemicals.
That's because you know what you're talking about. If you type Fortune 100 into AI, into like AI image generator, you get men in suits shaking hands with each other.
Right.
Visualize.
You asked the wrong person. No.
But yeah, you're absolutely right. So our biggest industries are, of course, really complex, but they're sitting on a foundation of chemistry, physics, and math. Drug molecules, fuels, catalysts, fertilizers, semiconductor manufacturing processes, molecules, reactions, materials. And so many of those microscopic foundations are overdue for reinvention, right? Like, either due to end of Moore's law or decarbonization or any number of reasons. We would love to be able to innovate much faster on those physical and chemical characteristics. The trouble is that conventional computers in general suck at simulating those things. And so those are some of the earliest applications where we believe quantum computers will give us the ability to precisely predict things that conventional computers could never precisely predict.
You make a good point. I mean, I guess it's because we've been writing about transistors and semiconductors for so many years. Probably people like me at some point just kept saying it's like a light switch and it's a 1 and 0, and over time this gets accepted and people feel like they have their head wrapped around it. But the spirit of what you're saying, at least as I interpret it, is that with qubits you're just able to tap into these properties of how the world actually works that we haven't been able to tap into before. So if we're talking about something like chemistry or molecules and how they combine, we're able to look at that problem through this new lens and get at like the underlying math that is at the heart of that relationship.
It's categorically different. It's not incrementally different. We want to unlock a categorically new level of mastery over chemistry, physics, and math.
And with the promise being that there are just calculations we cannot do today because we don't have a tool that lets us into this other level of physics.
Yeah, because when we try to represent those things with regular digital zeros and ones, all of the algorithms that we know about require extreme resources, like impractically large resources, longer than the age of the universe, or more transistors than there are atoms in our solar system or whatever, to represent the system of interest. And so it's, to all intents and purposes, impossible to answer these questions with regular computers. The most extreme example of that is code breaking, where our entire security and encryption is based on the premise that there are things that are effectively impossible to calculate with regular computers.
And encryption always comes up, so we might as well address it a bit. Like, to your point, I mean, this backbone of our modern trust in our computing systems, our financial systems, all this hinges on encryption. The idea is our current computers just are not powerful enough for anyone to really crack these codes. But people think with a quantum computer of sufficient size that it would be like minutes, right? To
I
crack
think
something like that.
That's pretty uncontroversial. It's extremely uncontroversial. If you build a big enough quantum computer, then you can break RSA and elliptic curve cryptography, which are the most widespread public key technologies.
Which is part of the reason the U.S. and China in particular, right, are charged. This is really seen as a very important field for that. If you get a chance to unlock a whole new avenue of science knowledge, you're heading toward a different future maybe than other folks.
Yeah, so I think again, with one or two exceptions, we're talking about a building scale machine. And that has been one of the pivots that the quantum computing space is sort of going through with a bunch of growing pains as we speak. All of these quantum computing technologies started out in university research labs, always, like it's some, experimental physicist like me or professor or something. And you start out with some benchtop experiment. And I think today, if you say quantum computing to people, that's immediately what they visualize. The chandelier, the famous golden chandelier, or some benchtop lab experiment. For more than 20 years, we've known that that's not actually a useful machine, that to get to useful machines, we need millions of qubits, and that's a building scale system. Now, I think governments are also starting to understand that technology like this actually has geopolitical significance, becomes a strategic sovereign capability. The fab was the first technology to really cement that in the heads of politicians. But obviously AI supercomputers are now seeing the same kind of dynamics. It matters where these things are built, and quantum computing is going to go the same way, both because of the encryption stuff, but actually I would say more so because of the economic promise of the technology. The drugs, fuels, materials, whatever that we spoke about earlier.
So journalists, or at least nerdy journalists like me who have covered some of this stuff for a long time, there is a degree to which we're emotionally scarred by quantum computers. I think I wrote my first quantum computing story, I don't know, it was probably roughly 16 years ago. There was a company called D-Wave. They were the first one that I remember getting a ton of attention as a quantum startup and getting funding. And I watched for the next few years as they just got
Yeah.
dismantled
Yeah.
by experts as this isn't a real quantum computer. And then since
Yeah.
then, huge names, like IBM, Google, Microsoft spending tons of money on this, chasing after, but it always feels like that thing that's 5 years away, right?
Yeah.
And we're always trying to make like a
Yeah.
few more qubits, and it's
Yeah.
like, and then half the time it seems like even when people do it, everybody in the field shits on each other.
Yeah. Endless mudslinging.
Right? Yeah. So it's always very difficult for me to tell
Yeah.
what's real and what's not. And then obviously you chose to do this as a career,
Yeah.
so I guess it has been so hard because it is a hard thing.
It's bloody
to
annoying.
do.
Quantum computing is really annoying. I agree with you. Like, the basic thing that I would say is that it's like AI. It's like the journey of AI. Billions of dollars of capital, and more importantly, to my mind, tens of thousands of years of human life have already been thrown into the pit of quantum computing.
Yeah.
And I start these talks now with this picture of a black hole. That's really how I visualize it. Just capital and life and time and our best scientists and engineers just piling after this thing for decades, as you described. D-Wave started 25 years ago.
Yeah.
And if there's one thing I take away from this, recent buzz from Google and Microsoft and others, like the gravitational pull of this thing, the promise of virgin territory, the promise of like categorically new capability, it's still pulling. Like it's showing no signs of stopping. People can see that there's a threshold which we can get beyond. And then, you've got all these different teams around the world, Google, Microsoft, Intel, IBM, Amazon, you name it, bunch of startups, national labs, universities, charging after this thing, all slinging mud at each other, all like desperate to tell you why their approach is the only one that will do it and everything else is horrible. I think, to that point, it's actually an anomaly that today we all agree on the silicon transistor. And it's maybe helpful just to think a little bit that that's a strange situation, that we all agree the silicon transistor is the right tool for digital computing. Of course, 50 years ago, that was far from the case. You had
because there were different materials
with like mercury cavities
yeah.
and acoustic memories and bubble memories, and they were all fighting tooth and nail over those different approaches. But it's definitely really hard to make sense of. It's definitely a frothy space. I think the basic mess is that you need 1 million qubits. And that was the orthodoxy of the field 20 years ago. So when I started out as an undergraduate student, not quite 20 years ago, but nearly, they sat me down in Leeds University and they said, Pete, the only reason that you are studying quantum information, quantum computing, is that Dorita Haronoff proved the threshold theorem, and it is known that you can do error correction for quantum computers. You therefore need about 1 million qubits, and then we can start to do profound things. That was the orthodoxy of the field. 1 million qubits, to put that in context, today Google has about 100 qubits in their admittedly very impressive system. And so, because it's hard to control single atoms, single electrons, single photons, because this isn't, easy going, it's led to an enormous amount of wishful thinking, basically. And I'm sympathetic to that wishful thinking. D-Wave's approach was basically to say 1 million seems like heaps, but if we put 1,000 qubits together, maybe something will come out of that. And actually, 25 years ago, I think that was a reasonable bet to make, actually. Let's have a crack at it and see what happens. What has happened in the last 5 or so years is that the world has swung back to, you know what? We actually need error correction. We actually need 1 million qubits. We're really talking about a building scale system. And you're now starting to see that being taken seriously by some of the more capable and sort of confident groups, I'd say.
Yeah, I remember D-Wave coming out and they're like, oh, we have, I forget what the first number was, I don't know, call it 12 or 16 qubits or something. And then they're like, we're just going to kind of go on this Moore's Law type thing. We'll just keep doubling and get somewhere interesting. What ended up happening, at least from my perspective, was that I would hear from these quantum labs is like, oh, we have 2 qubits.
Yeah.
couple of years later, it's like we have 4. Like, it just seemed like things were going a bit slowly, and this doubling was not happening. And then when people start talking about 1 million qubits in my head, it's like, oh God, that's many, 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 many years away, because it seems like people are struggling, even though we've got better at it, that they're struggling just to make bunches of qubits.
Yeah, so this is the origin story of PsiQuantum, basically, is that frustration and that disillusionment, basically. So our CEO, Jeremy, 25 years ago, was in Brisbane doing STM lithography. So taking an STM tip, like a little spike, picking up single phosphorus atoms and putting them into isotopically pure silicon one by one. And you screw it up and you drop the, I don't know, I've never done it myself, but had a total crisis of faith, pretty much what you're describing. 1 million, like, we're dreaming here. 1 million is a fantasy number. And it's easy to get that feeling when you're a physicist in a physics lab operating 2 qubits, as I was 12 years ago, just getting them working. And Jensen, of course, famously a few months ago, trashed the valuations of a bunch of public quantum computing companies by saying, what he said is 20 years, he reckons, for really useful quantum computers, whatever that means. The piece of his quote that went missing that to me was more sort of significant was he said, you need 1 million qubits, which again has been like brushed under the covers and sort of ignored by the field, I would say, for the last decade. Finally, people are back to owning up to that. So, the rationale is we need about 1 million qubits. Today, we've got about 100, Google, for instance. That's like a 10,000x scale up or 100,000x scale up or something. Seems like a multi-decade exercise to do that. Of course, like Jensen himself has the counterpoint, which is that the XAI Colossus supercomputer, Elon and co, famously has 100,000 GPUs and was built in 112 days. So that's 100,000x scale up in 112 days. That's a miracle. Like, what is the machinery behind that miracle? It's the $1 trillion in 50 years that's gone into the semiconductor industry. It's the fact that a fab is the pinnacle of human accomplishment technically on this planet. You can build billions of devices, they do billions of things a second, tens of thousands of wafers, and you ship them out like, nobody's business. That machinery is exactly the leverage that we were founded to deploy to get to 1 million qubit systems much faster than is conventionally anticipated.
So let's talk about that a bit. You guys started in
2015.
2015.
Yeah.
From the get-go, you made 2 large and different bets. One is that you can make qubits out of electrons, atoms, and photons. As far as I know, you're the only major player that has picked photons.
There are a few other people.
Okay.
Yeah, there's some great teams doing photons. We're the biggest private effort on photons.
And all in on light and making qubits out of photons, isolating a single photon and making it do the things you want to do. And then the other massive bet that you guys made was that most, if not all, of these other labs were focused on this year by year doubling of however many qubits they could make. And you guys were just like, we're going to raise hundreds of millions of dollars and we're going all in and we're coming out the other side with 1 million qubits, or we're not. Right? I mean, that was it's like, we're going to have to invent a ton of stuff along the way. We don't know if we can do it.
Front load the pain was the whole thesis of the company. And startups are told it's all about minimum viable product. Do not front load the pain. Under no circumstances go and establish high volume manufacturing first. We basically ignored all of that advice and with the understanding that this isn't a minimum viable product type of technology. This is a technology where the bare minimum, where, the threshold for usefulness, beyond which we believe you have an unprecedented, world-changing, lucrative technology, that threshold is really high. And you only cross that threshold if you are directly leveraging the most mature fabs, the highest volume contract manufacturers, et cetera, et cetera. And so, we, from the beginning, understood that we would have to invest into very high performing, very manufacturable, very scalable technologies. And that was in the face of a deep temptation to go and do demos, right? And I was thinking about like rockets in this example, where if you've ever launched a solid rocket, like toy rocket, you know, it's pretty fun, right? Like you get this 1 foot thing and you light it up and it flies and you see the thing go up into the sky and you say, there's my rocket.
Yeah.
And whilst you're doing that, you understand that you have solved none of the engineering problems that are actually associated with a commercially useful orbital, you know, launch system, right? And so in contrast, when you do a static test of when you see the static test of a Raptor engine, for instance, it's kind of unsatisfying and it doesn't go anywhere. It doesn't get off of the ground.
Yeah.
But that investment is a good use of capital, and that's actually brought you closer to a commercially useful machine. And so we were just always pig-headedly insistent. We're going to take these resources and we're going to establish the manufacturing process. We're going to figure out the networking. We're going to figure out the cooling. We're going to figure out the architecture. What we're not going to do is take the 2-qubit processor that I had online 12 years ago and is now in the British Science Museum, and hook that up to AWS, try and make $1 million of revenue, make a press release, bang on about breakthroughs all day long. We're just not doing that. That was a runway that was laid out in front of us and that we chose not to pursue.
You kind of annoyed people for a while.
Yeah, I mean, really annoying.
You were made of these British and Australian academics. You guys were all used to publishing some of the top papers in the field. And then for this period of time, you went super quiet. You're also like, we're just going to invent a bunch of stuff that doesn't exist and we're going to do it. And people, you know, I remember people were just very, very skeptical, and I think they were skeptical just of the size of the gamble you were making. But then also when you went quiet, it was like, oh, they can't, it's not working. They can't do it. Right. And then just over the last couple of years, still not tons, but you guys put out trickles of information about where you're at.
Yeah. I mean, I think, before we started the company, right, we'd already spent 15 years or so in the university system. Jeremy did the first 2-qubit gate for photons 20 some years ago in Brisbane. And we had this paper factory basically at Bristol where we were ripping out Nature papers and science papers and whatever. Yeah. The machinery of that is that we had started, Jeremy, Mark, and others had started with this idea of taking integrated photonics, silicon photonics that was originally developed for networking and data center applications, and repurposing that to manipulate our photons, right? So in the bad old days, the light would be bouncing around on an optics bench between mirrors and lenses and stuff. And that just, you know, was pretty limited. Yeah. They hit on this thing of putting that on a chip. Suddenly they could print chips and do entanglement and entangled state generation, and we did the first demonstration of chemistry on a chip and all these demo systems in the university, which sold like hotcakes, right? We were running that for a long time. When we started the company, we made this just like completely abrupt change of direction where we said never again, never again, basically, like we're going to do something very different. And that did upset quite a lot of people. And as you say, we also just started making deranged claims, right? Like, 4 guys, none of us real engineers, all like academics. Academics don't always have the best track record of running startups or running at startup speed, I guess. Yeah, first of all, heresy in that we were saying you need 1 million qubits, right? Like at that time, it had become very fashionable to say maybe 100 is enough, maybe 1,000 is enough. You know, maybe we don't need error correction. And that was well motivated, that there were sort of technical reasons why people wanted to believe that smaller systems would be useful. And we were kind of screwing up their pitch a little bit by saying, no, I think you need 1 million qubits. Yeah. So I think that was upsetting to people. And then even worse, we started saying really stupid stuff like, we're going to put superconductors into a commercial semiconductor fab. So not an R&D fab, not a bunch of scientists. We're going to go to a factory that is making thousands of wafers for cars and laptops and cell phones. And trust us, it's going to be fine. Yeah. We'll put the superconductor in there. And we're also going to get some national labs to give us access to like 30,000 square foot liquid helium systems. And the architecture, Yeah, we are going to have to improve that at an exponential rate for 6 years running, but don't worry, we've got that.
Yeah.
You know, claims that you should be bloody skeptical about those claims. We were skeptical about them, to be honest. But like, you have to do that. You have no alternative, right? Like, the alternative is to go and do some demos, publish some papers. And so we just, you know, all of us have been doing this our whole adult life. Like, it has to actually work. It has to be a real technology. And you have no alternative other than to solve those problems.
Yeah.
And so, yeah, that was provocative, let's say, to people. We didn't publish a lot of papers because we were really busy. But we managed to recruit really good people. And I think a lot of the really good people around the world ended up coming and working for us on the promise that they would be able to devote their life to the real thing.
To the thing.
Like, actually come and do it.
Yeah.
Yeah.
I feel like this next part may end up in an unsatisfying place because maybe it's just me and I always struggle with it. But when we talk about 1 million qubits and why we need 1 million qubits, you talk about things like error correction. I don't think most people know what that is, but correct me where I'm wrong here. I mean, qubits are hard. They have a tendency to want to fall out of the state that you want them in. So the idea is kind of, we make a shit ton of qubits, and then by making a ton of them, we end up with at least some much smaller subset of these that are doing the work we want to do. I mean, that's kind of the reason you need so many, right?
Yeah. So if you think about your laptop, chip in your laptop is running at a gigahertz clock, give or take. So it's doing 1 billion things a second.
Yeah.
Then if you think about any kind of like involved scientific calculation, calculate the structure of a molecule or do some optimization problem or something like that, it's taking some fraction of a second to give answers on those things. That's a very approximate statement, but give or take. It's not like 1 clock cycle, and it's not a year. So that's about 1 billion operations, right? Like, when we run classical algorithms for these kind of problems, it's about 1 billion operations before you get an answer to get the complexity of the problem sort of loaded into the machine. And it turns out quantum computers aren't that different. Like, for all of the useful quantum algorithms that we know about, we're talking about somewhere on the order of millions to billions of operations from start to finish.
Okay.
Now, with your transistor, you've got an error rate that is ludicrously low. So your cell phone basically never actually fully glitches, right? Like, the app might have a bug, but the cell phone itself is doing billions of things a second for years, and you never see an error. That's because the error rate in a transistor is like 10 to the minus whatever, 15 or something insane. The error rates in qubits, everyone's qubits, superconductor qubit, ion trap, whatever, they're all about 10 to the minus 3, maybe 10 to the minus 4 if you're lucky. That's kind of the state of the art. And nobody is optimistic that we're going to go significantly beyond that. So they're just so far away from each other, right? Like, the qubit error rate is a fraction of a percent. The transistor error rate is like 1 in 100,000 years or something.
Because qubits are just so fragile and difficult.
They're a fundamentally different object. Yeah, they're just a different object. They feel their environment very intensely. They're little fragile, delicate little objects. And so you end up with a higher error rate, and that means that we have to pay a lot for error correction in order to get to the millions or billions of operations that are needed for useful algorithms.
Okay, and then the thought is, if you make the 1 million qubit machine, you end up with what, like 1,000?
Give or take, So none of these statements are precise. It's roughly 1 million qubits. It's hundreds of logical qubits is kind of where you want to be, I think, is the general consensus.
And then you get those, and then you run this new class of algorithms. One super cool thing about this is, you're not talking about giving it a problem and having to sit there and wait for a year for some result to come out. It's sort of like it can be in a matter, I'm sure it depends what you're doing, but we're talking about minutes, right? For incredibly, for things we just cannot solve today, even if we had a computer the size of like Manhattan running for 100 years.
So Google, end of last year published results on their roughly 100 qubit chip.
Yeah.
The two results that they did were the first really good demonstration of error correction. And, obviously we compete with Google in some sense, like we use a different technology. I could talk about why we prefer our approach, but that was really an awesome result with those Google superconducting qubits. And it was awesome because there are a bunch of skeptics who said quantum error correction is a fantasy, like it's never going to happen, it's practically too hard, or it's forbidden by the laws of physics or something.
Just the idea that they'd just never be good enough to really kick out.
Yeah, it's really bloody hard, right?
Yeah.
It's taking that Google team a decade to get that system really under control. You got to control 100 little tiny microscopic devices. They're cooled by that chandelier. So to give a feeling for the cooling, they go down to minus 270 degrees Celsius, which is deep space temperature. And then they go 100 times colder still to 10,000ths of a degree above absolute zero. So you got this insane temperature, you got all of this, electromagnetic control that you have to do. It's a miracle of engineering. And, it took a long time. So skeptics started saying, this ain't happening. Kind of like self-driving cars, right? Like when I arrived in Silicon Valley, people told me self-driving car, you're not going to see it.
Yeah.
Like they'll get to 80%, they get to maybe 90%. There's no way they're getting to the safety and so on.
All the edge cases. And
so it was awesome to see that Google quantum error correction result, exactly the way it was supposed to work, very validating for the field. And then the other thing that they did in that experiment is they did a so-called supremacy experiment, where they're running a basically artificial benchmark to show that chip can calculate things that would take an extremely long time to calculate with a conventional computer. And the number that they put in the paper, I actually forget the term that they use because it's so ridiculous. Is Alex, are you there?
10 septillion years.
Septillion years, so 10 septillion years. I forget it because it's just ridiculous. Like, and of course they got panned by journalists for that. Septillion years, this is fraudulent nonsense, whatever. It's completely defensible, right? Like that chip indeed does calculate something that, as far as we know, a conventional computer is going to take some absolutely unthinkably insane amount of time to calculate. Now, that's a benchmark of no commercial utility, which is how they can squeeze it into 100 non-error corrected qubits. But yeah, like the reason that I'm spending my life on the reason that like tens of thousands of people like me are spending their entire adult career on this is that it's not an incremental technology. It's not a 5x advantage. It's unlocking almost unthinkable, categorically new type of computer that, we expect to have profound impact. And if that wasn't the case, and if I ever find out that that's not the case, then I'm going back to England.
Yeah, like how pissed are you going to be next year when ChatGPT is like, this is how you should have built it?
Yeah, so, I mean, in fact, you saw the only place that we use AI in the whole company earlier today is we're proud actually to, hopefully, I aspire to have some of the DNA of a semiconductor company, right? Like bad coffee, polystyrene ceiling tiles, a lot of like just hard work, and only the tiniest amount of AI reluctantly in the system.
Yeah. Is there a chance that the?
I need to change battery.
Oh
No, you're good.
I won't torture you too long.
No, we're good. I'm
Okay.
in good shape, and this is fun. I love these shots. They look
Pretty
great.
good, right? Yeah. We're cool. Will you be? No, I was wondering if the superintelligence lights up next year. They're like, you morons, this is how you build a quantum computer. Yeah, would that feel good? That you don't have to work quite so hard on this anymore? Would you be pissed you didn't get to see your life quest through?
Yeah, so I think, it's a good provocation. So back to the point, right? Like, I think that quantum computing has the same or very similar trajectory to AI, which is that people knew that neural nets were a good idea decades and decades ago.
Right. And they kept falling in and out.
And they had multiple winters, and DARPA defunded AI, and a lot of pain and suffering. There were times where you wouldn't even admit to being an AI researcher because it was this shameful, failed.
Not too long ago.
Not too long ago, right? So like, how did we arrive in the madness of AI today? From my point of view, which is biased, there's two magic ingredients. The first is exponential improvements in the architecture sustained over decades.
Yeah.
So just grinding away at the mathematical formalism and how you actually implement these machine learning methods, transformers and attention, which, by the way, LinkedIn is the best place to read about that these days if you want to learn about transformers and attention. But they just ground that thing slowly to something that was way more efficient. And then the other thing that happened was borrowing somebody else's hardware. So GPUs from gaming, of course, suddenly unlocked this thing that then got above a threshold of usefulness, where now we've got the world's most valuable company, etc. And our view is, of course, that quantum computing follows the same trajectory. We've been working on these architectures since the first architecture for optical quantum computing, 2001, Knill, Flammen, Milburn. We've been making that exponentially more efficient year on year on year on year. And that's the work of our architecture team today, is to continue on that trajectory. Are we expecting some sudden breakthrough? No. And again, like AI, right? Like, you see these papers and they say, we've suddenly discovered how to reduce the resources for a transformer by 1000x. And then when exposed to sunlight, you see that it's not quite as good as the paper claimed. That is a slow grind, really, to make those things better. And we expect quantum computing to follow the same trajectory. And the whole space is poisoned by breakthroughs, right? Like, if you pick up a newspaper and read about quantum computing, it always says breakthrough in the headline, like breakthrough in entanglement generation or breakthrough in error correcting codes or whatever. Like, think about real companies that actually made useful technology. TSMC, ASML, SpaceX, NVIDIA, Waymo. Did they get to where they are with breakthroughs? I don't think so.
No, it's a grind, right? It's like a 20-year sort of process. Yeah. I mean, I was just going through them in my head. Little like breakthroughs here and there, right? But didn't have to invent like a fundamentally new sort of thing. It was just make the stuff work.
Right. Yeah. So, like, of course, there are some sort of discontinuities in their trajectory, but quantum computing, like, it's way over rotated on breakthroughs.
Yeah.
The idea that, even that Google result, right, like, was described as a breakthrough in quantum error correction. Really what that was 10 years ago, they said, we got to implement the surface code. We need to make 100 qubits and we need to get their error rate below X. And then they just ground it out for a decade, right? And they got it boringly to where it needed to be. And then there it is. And
I think it's probably like a function of, this has been this very academic thing that's only relatively recently entered the startup funding world. And so everybody still talks about the breakthroughs based off these Nature papers and stuff like that. But if you're really trying to become an industry, you've usually put some distance between your Nature paper and your big product. You put a lot of distance between that coming out. So I appreciate that you guys have always been trying to steer things a little bit more this other way. It is a hilarious field too, because you guys all come out with these things. Everybody universally like shits on each other, and then there's like begrudging respect on like some minor points of it, you know. But like when you're in my shoes, it's impossible because every single company is sticking up their hand saying they're the only ones who've pulled off the miracle, and every other person is saying they're liars and totally full of it. And so you're just like, man, is anyone doing anything? I have no. Like 15 years ago, I was all optimistic, and then now I'm kind of like, I actually have no idea if anyone is telling the truth or sort of where the base is. You know,
So I mean, maybe two things on that. One is that there are really good reasons to be optimistic, and the first is that everyone now is making qubits like breakfast cereal, right? Like 5 or 10 years ago, you got one qubit going. That was like Nature paper, cause for celebration, finish your PhD, everything's amazing. Now it's like, oh, obviously you've got a qubit. Like every platform superconducting qubits, ion traps, photons, quantum dots. Everyone can make pretty good qubits. They're showing pretty nice 2-qubit gates. Some of them are really nice. You'd like to make them a little better, but like that's just sort of, table stakes at this point. And then even some of these 100-qubit processors are kind of doing impressive things, error correction being sort of the most important one. And then secondly, like the whole space is pivoting from this kind of obsession with demoing a 50-qubit processor on a cloud provider to like, shit, we got to build the real thing.
Yeah.
And you're seeing people kind of reprioritize towards the stuff that we've been obsessed with forever, which is like manufacturability, cooling power, connectivity, control electronics, scale up. Like how do you actually build a real machine? That's really healthy for the field, and that's across the board. Everyone is now starting to behave in that way, which I think is just awesome.
Yeah.
And then, as far as like the scrutiny and the, endless mudslinging, and
You guys are so mean to each other.
everyone's so mean. Like, first of all, again, like I think the fact that the semiconductor industry, or at least like people aren't doing that over transistors very much, that's actually an anomaly.
I'm sure it used to happen too. I mean, the closer you get to scientists being scientists, the more they're actually. I kind of appreciate it. They're willing to actually like say stuff, but they can be quite nasty. Yeah.
But so one thing that is going on is the DARPA utility scale or quantum benchmarking initiative. So I always just think about this sort of like bathtub curve where if you want to get a feeling for what somebody's doing, the first 20 minutes of talking to them is like mega valuable in terms of like time to information ratio. You get a feeling for it. You're like, okay, this person is full of it. This person is really serious. I don't understand any of the technicalities. And then there's this sort of like long period of trying to learn the basics of even the framework for how to think about what they're doing, which takes a long, long time. It's very involved, and where your learning rate is really low, right? Like you're actually not getting any good signal on, okay, is this real, or is this really far away, or is it pretty close, or where are the specific risks? Which risks are they hiding? And it's a long way before you get out the other side and really get a grip on what the hell is this person talking about. And I think the DARPA QBI effort has been really well structured to deal with that problem. So that was set up as a red team. So to the beginning of our conversation, rather than the default, which is that a government says, we love quantum computing is awesome, it's a strategic priority, we want to fund quantum computing. Joe Altabita at DARPA says, he's been around quantum computing decades, says, I hate quantum computing. It's doing my head in. It's the most annoying field ever. These guys are all claiming that they're going to do it. And so QBI started from the premise that quantum computers are bloody useless, no commercial utility whatsoever, not going to be worth any money, and no one's got any idea how to build one anytime soon. That's the starting premise. And then it was set up as a red team activity. So basically we're going to get tens of scientists and engineers from the national labs, from universities. We're going to build a team inside DARPA, and we're going to go and attack these claims and try to kill the bad claims, basically.
Okay.
And we're going to pay to do that work. That to me is like a very smart way to deal with the kind of frustration and madness that you're describing. And we've been engaged in that program for a few years now. It's been awesome for Mercedes, who you met earlier, and for the whole team, just to get exposed to that kind of aggressive scrutiny, deliberate red teaming of our claims. Yeah, it's been great.
Okay. And then on the plus side, there's a reason we're in this building with this fantastic backdrop. You guys are there's lots of what you're doing that looks very, very real. You know, you're breaking ground in Australia at a massive site that's being backed by the Aussie government. You're breaking ground in Chicago at another massive site. So both of those are efforts to start building this roughly 1 million qubit system. And then we're in Silicon Valley right now at, like, this will be kind of a hub of R&D for you guys to dial in the hardware that will go there, or just to advance keep making
Yeah,
this
so
more
it's
real.
really for
and-
scale up
Okay.
of production of the more extreme or bespoke pieces of the system that we build.
Okay.
So yeah, like, quantum computing holds itself back by endlessly marveling at the kind of science fiction characteristics of what we're doing. And I love to do that, right? We've got superconductors and alien technology all over the place. PsiQuantum has always done well in sort of basically choosing to look at the other side of the equation, which is it's silicon, it's glass, it's metal, it's welding, it's pipes. Get on and build it and improve it until it meets the spec. And we've been doing that so far in our headquarters over in Palo Alto. And that's we're proud that that is honestly a pretty scrappy, rough environment. Polystyrene ceiling tiles and bad copy
labs
and hundreds,
everywhere.
hundreds of people. That was all conference
Yeah.
rooms when we showed up.
Yeah.
So there was no lab space. We built out basically. So the landlord, very nice landlord, when we first met them, said, "This is our beloved building. We've had it for decades. You gonna put any hardware in the building?" And I think me and Jeremy looked at each other and said, "Yeah, maybe some." And now the whole place is just overflowing.
No conference room is safe. Yeah.
We're proud that we make beyond state of the art photonics, cryogenics, whatever, out of that small space. But with the impending build out of these large systems in Australia and Chicago, it's ludicrous to think that we could do it in that space. So this is about a 10 times larger facility, much better cleanliness, temperature control, thermal control, and heaps of infrastructure already in the building. And this is where we're going to scale up production of the BTO, production of the blades, fiber attach, and we will also run some intermediate scale systems in this building. So we'll actually have arrays of cryostats running inside this facility. So we're not having a full-scale quantum computer here, but this is really for scale up of some of the pieces of the system. We always seek as much as possible to outsource, contract manufacture as much as we possibly can, but this is for the kind of exceptions to that rule. So BTO, for instance, we're the only people in the world who make a 300 millimeter BTO wafer. We got to scale that up ourselves in this facility.
So, when you guys set out, you raised quite a bit of money from the get-go, as far as I remember. And then, so you're coming at people with this pitch. You're like, look, everybody else is doing this. We're going to go build this thing. That's already, it's going to be expensive and high risk, but potentially high rewards. So I can wrap my head around some of that. It's good to do something different to what everyone else is doing. But there's these pieces that you guys have done along the way.
Yeah.
Like an optical switch that nobody had ever really designed before to route these photons about on a chip. You had to figure out cooling systems that would work on this chip that nobody else had figured out before. All kinds of things.
Yeah.
And each one of the, not each one, but there's a handful of things where it's like you didn't even know if you could invent the thing and invent it on any kind of timeline that would match up. How do you possibly talk people into, it's 5 or 6 things that you're talking people to believe that you can do?
Well, I think there's a few things to say there. Obviously, we've been, I think we made a good bet when we started the company that you would need 1 million qubits, that photonics was a good way to do that, and that leverage of high volume semiconductor manufacturing, contract manufacturing, et cetera, was really a key to get to big systems quickly. And I think, there's a bunch of people for whom that's anathema and they didn't like it, and that's cool. And there's a bunch of people for whom that immediately made sense and who wanted to support us. And of course, that wasn't coming out of nowhere, right? Like my 3 co-founders were all full professors of physics and electrical engineering. We had tons of Nature papers under our belt. So we had some credentials when we started the company. And yeah, definitely take it or leave it kind of premise, not a friendly framing for what we're trying to do. You're right, we've raised, relatively speaking, a lot of capital for a startup. I'd also reflect that if there are SaaS companies making apps and whatever else that have raised a lot more money than we have before they were profitable and who aren't,
They
you
don't
know,
do shit. They don't have to invent anything.
making the biggest cryostats for quantum computing ever made, and putting 10 pickup truck sized
like
manufacturing tools in a
marketing's
fab and
not
so
cheap,
on.
man.
So we're pretty, I think, we have things to justify the expenditure. And then, again, TSMC, ASML, SpaceX, NVIDIA, Waymo, right? Like, these are the legendary companies of like my generation. They're all doing insanely hard technology that at one point was widely doubted as fantasy. You're going to catch a rocket out of the sky. You're going to drive these cars across the city with nobody behind the wheel. You're going to get to 3 nanometer transistors. You got this bloody particle accelerator in a box that you're trying to put in the fab. Just nonsense, fantasy stuff. And those are the enduring companies. Those are the companies that everyone wants to be, right? And so like we have a real opportunity to build that kind of legendary organization here. And I think that's what our supporters and our employees and our team and everyone around the company, the partners that we have for the company, that's what people see. And they understand this is very new and unproven, and there's endless hard things that we have to do to get over the line. But again, like that's how those examples that I listed got built. And this isn't against the laws of physics. There's no reason you can't do this. Get on with it. Like, spend your time as efficiently as possible to get above the threshold of utility and unlock something actually new. That's what we're here to do.
I think what I've heard you guys talk about this, we break ground in Australia and Chicago this year, and the goal is by 2027
so we want to have the site operational end of 27.
So, and then I've also heard you talk about, look, we feel like we've solved a lot of the science part and this is moving to an engineering project. Like, what are the odds though we get to 2027 and like, how confident do you feel we turn this thing on and it's calculating, or are there still plenty of things that have to be figured out?
So obviously we're building a building scale machine with a completely new kind of computer in it. Cryogenics, superconductors, optics, gigahertz, you name it. It's bloody hard, right? Like, it's one of the hardest things humans have ever tried to do. I'm lucky to be surrounded by a team of people who have done things like that before in their lives, of people who aren't physicists like me. And this is, you mentioned the trope, which is this used to be science and now it's engineering, right? Like, people love to say that. They love to say to investors, my thing used to be science and now it's engineering. And they expect people to say, oh, great, let me get my checkbook out, right? One sort of litmus test for that is the team. Like, if your team is almost all scientists, chances are you are doing science, right? If your team is majority engineers, as is the case with PsiQuantum, maybe there is at least a hope that you have managed to graduate that out of the regime of science and into the regime of engineering. And indeed, if you look at like where we spend money, where we do work, a lot of it is categorically engineering work. It is iterate on the losses in a waveguide, iterate on the glues that we use to connect things together. There's just an enormous amount of work like that going on. And then, like, as far as my confidence in the activity of the company, we've historically made these claims that that stretch people's imagination a bit, right? Like, again, we had to put 10 pickup truck sized semiconductor manufacturing tools into a commercial clean room with superconductors in there and get that into a 35 layer 300 millimeter manufacturing process. We did that in about 2 years. And most people would have been completely justified in saying, you're mad, you're not going to do this. And we did it. And obviously now we're heading further into unexplored territory. But I think we have a serious plan. I think we've had external parties, DARPA, as well as our vendors, as well as like all of the partners who we deal with, of course, scrutinizing that plan to some extent, testing like how confident really are we in these claims. and we're just going to get on and do it. There's nothing else to do other than to measure our risks, de-risk things where we can, and get on and build these things.
Yeah.
And that's just served us well. Like, I can sit here and, marvel at the mysteries of what we have to accomplish, or we can cut some metal and make some silicon and do some measurements and do some math, and we choose to do the latter.
And if you guys are right and you pull that off by 2027, if you look at the strategy of your major competitors, there's really nobody else that has some concrete plan for a 1 million qubit system. I don't know if you'll choose the polite road on this or not, or and you still have to prove that you can do this, which is the hardest part. But at least in the nearish term, aren't your competitors sort of screwed if you guys do pull this off? I mean, there's just nobody else who really seems to be doing that.
I think that, again, like, with very few exceptions, people in this space are in it for the long haul, and they really, that vociferous disagreement and mudslinging that you described is genuinely motivated by people who actually believe in their thing, right? Like, those people believe in what they're doing with the same conviction that I have for what I'm doing. And you have to be respectful of that. And I take seriously, like, those guys are pedal to the metal, and they are not forbidden from accomplishing that by the laws of physics. And they obviously know things that I don't know, and they're going to barrel along, and good luck to them, right? We're all going to need it. But do I think that this is a race where Team A crosses the line and then Team B crosses the line and then Team C crosses the line? No, I don't think that hard technology like this has the dynamics of a race. I think it has the dynamics of a filter. And there are many different ways in which you get filtered. Your technology, your ability to graduate through different layers of maturity, even, unfortunately, dumb things like funding and team and so on. All of that has to be successful for you to get out the other side. And I think that does lead to dynamics where there's basically one TSMC, there's basically one ASML, there's basically one Waymo. And our ambition, which we have not yet proven, to your point, is to become that company.
Yeah.
And I really think we have a shot on goal to do it. And I think that I'm pretty sure those companies didn't spend much time thinking about their competition.
Well, I mean, it was roughly a month ago, I think. I mean, Satya Nadella was holding up.
Yeah.
I mean, it was one chip, right?
Yeah.
Yeah, and he's holding up this one chip, and the world's celebrating that Microsoft is back in this, is very much in this competition. And then, I mean, I'm not trying to go easy on you guys, because I think you still have incredible amounts to prove, but it's a fundamentally different strategy to have somebody holding one chip in their hand, and then we're sitting in this building is even, this is a fraction of the computers that you're starting to build.
We're barreling ahead. If you read our Nature paper, it's explicit. The components on our chips today are not good enough.
Yeah.
We're still improving the performance of those components. We got a list.
So the components are not good enough to make the
tolerance.
2027 system run the way you want it to.
That's right.
We still
got a gap.
There's things that have to be solved.
But what is the nature of the technical work to close that gap? It is not breakthrough science, right? It is continue to improve some, mechanical property of a device or some optical property of a device, where we've been improving that at an exponential rate for whatever, 3 or 4 years.
Those people just aren't allowed to leave the office.
To first order. To first order, yes. Like, that is basically how we see it. So again, like, we're clear, like, it's extremely difficult to build this machine, no questions. But, like, what can I do about that? Like, what can I do about that other than
push forward,
get on with it, move forwards at the maximum pace that is reasonable? And like, the Microsoft group has been doing amazing work for 25 years, and clearly currently really excited about what they've got. There's just no action that I can take on that other than to ask our team to continue at the insane pace that they're already maintaining,
Yeah.
maybe go a little bit faster. I don't know.
Well, and I honestly don't mean this question to sound as like pro PsiQuantum as it is. It's just when I'm trying to figure out everybody's end game. So when
Yeah.
you look at, call it whoever you want, Google, IBM, Microsoft, like you guys must fundamentally think they've made a miscalculation, a mistake, if you
Yeah.
are able to do what you think you can do.
Yeah, of course. And that's not a derogatory thing to say. That's just an honest
Yeah.
thing to say. Of course, we believe in our approach and they believe in their approach. Like, again, I really think like self-driving is quite a helpful framework for this. Again, lots of doubters, justified doubt and skepticism, lots of different approaches, vociferous arguing about LiDAR and things like this.
Tons of money.
And, you know, I actually take quite a lot of inspiration from Waymo in this respect, in that they were extreme, I think it's fair to say. Like Waymo, from the beginning, and you'll have a perspective on this, which I'd appreciate, from my point of view as a novice into that space, they were quite extreme, right? Like they from the very beginning said, this is a grand endeavor. This is not a quick and easy exercise. And I think that's put them in a pretty special position in the space. And I'd like to think that PsiQuantum has some of that DNA, where we understood from the beginning, the bar is really high. Your performance has to be insanely good. You cannot do this in your backyard. You have to be in a commercial foundry, et cetera, et cetera. I think that's put us in a pretty good position, yeah.
This is a gross characterization of entire peoples, but there are some academics.
Okay, that's fine. That's allowed now.
There's
Comedy is legal.
It is again, yes. There are some academics I know who have gone on to run what I would consider like high risk startups, because sometimes the academic, the British Aussie academic combo, not like a long track record. Yeah, of often in my experience, that grouping, it like has a little too much academia still in it. I'm just thinking of sometimes I go visit Oxford and Cambridge, and I see these very, very smart people in the start. It's not the same vibe as like a Silicon Valley startup. And you guys have been sequestered in Palo Alto for many years now. So I'm actually impressed you've got as far as you have it, that you guys did. I'm actually impressed that you stuck to because it is always tempting.
Do something smaller. No.
Yeah.
It's too hard. You do something easier, do something cheaper. Yeah, I mean, that has been the refrain for nearly a decade.
And in my gross characterization of not just peoples, but professions, I noticed, the more academic-minded folks, I feel tend to be a bit more conservative and pull back.
So, like, I think, if you'll let me philosophize on this for a second, right? So all quantum computing companies are started by university academics, always.
And lots of semiconductor companies going back, but
yeah. I'd say quantum computing is very extreme in that respect. And there was always a risk that we would raise venture capital and build an extension to the research group that we had at Bristol.
Right.
And we were painfully, maybe excessively cautious of that risk. That's part of the reason we didn't publish papers, go to conferences, and maybe made ourselves slightly unpopular early on.
Because you fall into these old
Which said,
habits.
we're not doing, never again, we're not doing that. But, obviously, like, I'm confident in what we're doing, and my colleagues are confident in what we're doing. And if I were an observer of this discussion, it would be natural to say this guy is overconfident. I would understand that. I think there's a thing that is sorely underappreciated, which is that there is obviously risk to confidence. If you're overconfident and you're wrong, you cause a large explosion. And I am painfully aware of that risk. But the thing that sort of I think is underreported is the enormous amount of damage that is done by insecurity, basically, by, not fully committing to the task at hand. And that just slowly bleeds away $10 million at a time down the drain. And actually, I think if you accounted for the damage done by that machinery, it would be much greater than the damage done by overconfidence.
Yeah.
And I'm, painfully aware of the risks and the challenges of what we have to do. But I'm pretty sure that the right thing to do is to take those challenges seriously and go and solve them and not half-ass it, and that self-confidence is, I think, is like an important part of the DNA of the company. My co-founders, unlike me, were all successful, established, late-stage professors of physics and electrical engineering when they started the company. They all moved their lives and families to California to start the company. They didn't stay hanging around at the university. They fully committed, and they could afford to do that because they completed the level. They weren't halfway through the level of being an academic. They had finished that. They were publishing these papers, going to these, whatever. And they could say, you know what, I actually want to spend my life on the real thing. And I'm very grateful to be immersed in an environment where that is the default. My co-founders, the early employees of the company, and everyone who's joining PsiQuantum is, self-selecting basically because of the aggressive, sort of slightly extreme positioning that we have. That disqualifies us with a large category of people, and I'm fine with that. I think it's great.
I think I've got 2 last questions. Everyone okay? You okay?
Yeah.
Okay.
I'm going a bit too off-piste, but...
No, this is great. Those are my favorite parts. I don't know how to express this, so I don't know how to get this across to people, but when I hear quantum computing folks talk about how you get the answers out of this machine, it sounds like this very mystical process where you send it a problem.
Yeah.
Entanglement is happening. All this quantum things are taking place, and then it's kind of like not producing the exact answer, but it's honing in the range of answers you're looking for, and then you're sampling out of this thing to get the answer. I mean, can you try to explain how this works in somewhat humane terms?
Okay. So what you just described is the waffling bullshit that is widely and appropriately associated with quantum computing.
Yeah.
Let me try and diagnose that.
Please help me.
And I'm going to go a little bit back to basic. The double slit experiment.
Yeah.
The foundations, like Feynman said, all of the mystery of quantum mechanics is contained in the double slit experiment. Where was the electron when it went through these 2 holes? Right, we got a wall with 2 holes in it. Where was the electron? Was it in this hole?
Yeah.
Like a rock? No, because I see an interference pattern. Empirically, I see an interference pattern. It could not have been just in one hole. Was it in the other hole? No, by the same argument. I see interference. It can't have just gone through one hole. If it just went through one hole, there would be no interference pattern.
Okay.
Maybe it goes through 2 holes. Mystery, spooky, being in 2 places at once. There's nothing mysterious about that. Sound can go through 2 holes at once, right? Like a water wave can go through 2 holes at once. Piece of string can go through 2 holes at once.
Yeah.
So let's say maybe the electron goes through 2 holes at once. Let's test that empirically. Put one detector in one hole, one detector in the other hole, and wait to see both detectors go click. We never see any such event. So empirically, the electron did not go through one hole, did not go through the other hole, did not, by experiment, go through both holes, didn't go through neither hole because it got to the other side. At this point, you are screwed. Like, your natural language description of what is happening in the most basic piece of quantum physics is completely elusive. You failed. And this is why people talk about shut up and calculate as my preferred interpretation of quantum mechanics. Like, you ain't escaping from that. The mathematics, again, fits on a business card, let alone a postcard. It's the simplest piece of mathematics you could reasonably hope to deal with. And the natural language explanation of even the simplest experiment has remained elusive for 100 years. That elusiveness of the natural language explanation of quantum mechanics bleeds through to an elusiveness in describing how quantum algorithms actually function. It is quite difficult to really convey what it is that they're doing. But practically speaking, we program the quantum computer in Python. It's not some like mad programming language. It's Python. It's like really friendly, easy programming language. There is a gate set. We basically compile the algorithms that calculate the properties of molecules or materials or whatever into little sequences, little patterns of operations that are being applied to these qubits in sequence. And those then turn into boring old voltages in a silicon germanium or silicon chip that's then controlling the photonic chip inside the machine. The machine does a dance. Eventually our detectors go click. That gives us a voltage, and that voltage is a 0 or 1, which encodes the answer to our profound question that we're answering. So the machinery of the thing, it's bits of silicon and wires and voltages and boring old Python. And the magic of the thing is quite hard to describe in natural language for very fundamental reasons, in my opinion.
So this is kind of like this disconnect, because anytime you read a mainstream story, and look, I have to write these things and I try to do my best, but it's always the same thing. It's a regular bit is a 1 or a 0, a qubit can be both.
Yeah.
It can be,
so it does everything in parallel.
Right.
So it's like it tries every answer in parallel. It's like the classic deeply flawed explanation that is given. And then, so you'll read that article that says it tries every answer in parallel. And then you'll read the next article that says, no, that's bullshit. That's a terrible explanation. And both of those articles leave you completely unsatisfied at the end. So like, I wanted to convey why that is. Like, why is it that after 50 years of journalists trying to write about quantum computing and quantum physics, is it still so frustrating?
Just that our language, it sort of doesn't suffice for the job at hand. I remember...
Our greatest philosophers are still arguing, but a little bit like they're arguing over approaches to quantum computing. They vociferously argue over how you should interpret quantum mechanics. And then, so like my best serious effort to give a feeling, at least, for where that power comes from is, again, by analogy with chess. You start playing a game of chess with somebody, you have some established rules, which are basically the laws of physics from Maxwell and Newton, 100-year-old physics, and suddenly your opponent introduces some new physics, some new operations that they can do with information, some new rules to the game of chess, and now you are absolutely screwed in that game, because even with just 1 or 2 extra operations, suddenly they're playing strategies that baffle your mind and you're finished. And so that I think is a fair analogy for where the power of a quantum computer comes from.
You can slow time and move in dimensions that everybody else can't.
And again, like, once you express this as mathematics and code, it's a few pages of Python. And my favorite piece here is Martin Shkreli.
God bless him.
God bless him. Martin Shkreli, fresh out of prison, is now implementing...
Dude can do anything.
Implementing Shor's algorithm on real quantum computers.
Yeah.
Right? Like, that's the state of quantum computing.
Yeah.
Is that guy is writing some couple of pages of Python.
Yeah.
Executing that over the internet on a genuine quantum processor somewhere in whatever, New York probably, and getting answers. Now, still, that's too small of a system to be useful or worthwhile, but there's no actual mystery in that. It's a piece of aluminium and a bunch of helium and some Python, and you get some answers. And if we can just scale that up, emphasis on just, then we got something.
It's not that it's any more satisfying, but this is actually not unlike AI either, in that half the time I talk to AI researchers, well, all the time, it's like nobody actually knows what's happening inside of these models, but we give them algorithms and stuff comes out the other side, and it's like not only do we not know what's happening in there, we don't have words to describe it because we don't know, but something's happening, and it's different to what happened
philosophizing
before, right?
yeah. I mean, so like low bit depth and some of these moves that they made where the consensus was the machine is not even going to work after you've made that change, and it still works, and then they're waffling as far as what is the actual function here. Yeah, there is a reasonably strong analogy there, although I guess the distinction that I would make is that the actual physics of our devices,
like, you get that part,
the natural language interpretation of the physics of a quantum computer is still hotly debated.
Oh, I see.
The mathematics is rock solid, utterly uncontroversial, mundane mathematics.
No, I guess, I'm with you. I hadn't really thought about it. I always get frustrated by quantum, but now I'm realizing this is not unique because there's all these things in our world that have gotten so complicated and sophisticated
and this is also why, we're not, so we do take a very sort of provocative, extreme approach to getting a machine built, which is anti-incrementalist, basically. But we absolutely have intermediate scale systems. We're already running our PsiQube system in the UK. That's a big box like this, cooled to liquid helium temperature, bunch of chips inside, heaps of single photon sources, single photon detectors, etc. We're now building our alpha system here in California, and you saw the bigger fridge that we're using for that system.
Yeah.
And we'll build our beta system and so on between now and the first machines coming online. And we'll learn a lot from operating those machines, and I'm sure there'll be surprises in the operation of those systems, which is why we do it. And in that whole process, am I gonna answer the deep philosophical questions about quantum mechanics? Absolutely not. But are we going to be able to run these systems? I don't see any reason why we shouldn't. Yeah.
I think this might be my last question, but you guys had these big announcements about Australia, Chicago. There's on the order of like $1 billion to fund these things in both sites, I believe. Can you give people an idea of the scale of the system you're trying to build in both locations, and just the timeline for what this is hopefully looks like?
Yeah, so these are deals with the Australian government and in Illinois, in Chicago, where we're building our first utility scale machines at those sites. So the first system will be in Australia, and then hot on the heels of that, we're building a system in Chicago. And these are intended to be, commercially useful, full-scale systems. And these are building scale machines. So they are going to look like a conventional supercomputer or a data center, big facility, on the order of 100 cryogenic cabinets inside those machines. And we're breaking ground on those sites in the next few months.
These would be, these are major bets, obviously, both locations have made to try to be at the forefront of, if this works, be at the forefront of quantum computing.
Yeah, that's right.
Because it's no joke, right? It's like,
it's about $1 billion. It's a sacred responsibility for us to actually, deliver on what we're planning there. And we're just gratified that people want to support us in what we're doing. And our responsibility is just to execute as fast as humanly possible, as efficiently as we can, and get those systems built. And again, we have intermediate milestones along the way before we get to those full-scale machines. But yeah, we're really excited to be in this position. There's a parallel universe in which I stayed in the university, and me and my co-founders stayed there and published papers forever. And we would just never have actually been contributing to realizing a useful technology. And for so long, it has been apparent to us that this has to be a building scale machine. And so the question has always been, great, who is your fab? Who is your contract manufacturer? Like, have you made a few thousand wafers of silicon yet? Do you have the materials that you need? Have you figured out how the hell you're going to cool this thing at scale? And can you tell me where you're building it? Like, tell me, where are you actually for real building a machine? And when are you breaking ground? And these questions have been unanswerable by us for quite some time. We're now getting to the point where we can actually answer those questions. And yes, there are still enormously difficult things that we have to do. Our schedule is insanely aggressive, but it's really exciting to now be in the position where that is what we are doing. We can answer those questions concretely, and we're moving forwards. Yeah.
That was great. I think you feel good about that. Good.
Yeah.
One, I,
Yeah.
well, I've already answered this, but you guys reach 1,000,000 qubits, 2027. Like, what in your head? What do you fantasize? What's going to happen?
Oh, yeah, that's-
like 6 months.
That's a good question.
Yeah.
It's very good.
And just on that too, there's a bit into like that's where things start. It's not like Jensen stopped with the first
Yeah.
10 GPUs.
Yeah,
what
yeah.
happens when you build 10 million? You know, like is there aspirations or plans?
Yeah.
Because often it gets so bumped down.
Okay, those are great. Are you okay? Or
Yeah.
okay.
Yeah.
So everything goes perfectly.
Yeah.
It's 2027. You turn these machines on. I think people naturally assume magic starts happening right away. Like, what do you picture happening in your head in the first few months if this works?
Yeah. So, those machines are spec'd to the best of our knowledge to exceed the threshold where they are then actually solving commercially valuable problems that we could not solve with conventional supercomputers. And so these are intended to be commercial machines first and foremost. And right now we're working with a whole bunch of the usual suspects, Fortune 100 type car companies, aerospace companies, materials companies, etc. And these organizations are, developing batteries, developing drugs, whatever, and hope to use a quantum computer to accelerate that development. And so the reason that we're working with them right now is to make sure that they're ready to go when that machine turns on. And so we want to have the Python written, we want to have the algorithm optimized. There's a bunch of work to do to actually get all of that into a good state and be ready to go. And then, the problems that we expect to run on those first systems are mostly materials and chemistry problems that we think are exciting in those early systems. Of course, that's a pretty broad scope, right? If you think about all of the things that we do with materials and chemistry, it's pretty exciting opportunity. And we're obviously down selecting, right? Like we're trying to weed out which are the problems where it's the best possible fit for that hardware, where the advantage is the most profound, where the opportunity is biggest. And that's still work in progress to narrow down on the most interesting applications of the machine. That's why we work with these partners today.
I was hoping for a portal to a new universe, but
So to that point, no, you'll have to wait for that. Maybe next company. But
that startup is down the road.
yeah, that one's down the road. But no, so I think the important point here is like sometimes people think about quantum computing as a mass adoption type technology, and it's nice to imagine that this is going to be used by millions of people, but I think that's just a red herring, right? And again, if you think about some of the companies that I was listing, TSMC, ASML, SpaceX, like how many people have ever actually done a tape out at TSMC?
Right, it's relatively
How many
few.
people actually operate an ASML machine? How many people design a payload for a SpaceX rocket? It's like a tiny fraction of humanity who directly interact with the technology. And it's the second and third order products of those extreme capabilities that end up actually impacting people's lives and having a broader economic impact. And we see quantum computing as a very similar kind of technology. Also, like AI supercomputers, very few people are actually running code directly on that system.
Yeah.
But It's the second and third order effects of that new capability that end up being important for people's lives. So
You just gotta make like quantum chat GPT.
no, so no, the thing about GBT moment is that we all did it directly, right?
Right.
Like we all jumped on the web browser and saw how amazing it was. You're not going to have that with quantum computing, right? Like Jensen, and to that point, of course, Jensen was selling giant GPU clusters to no fanfare at all well before the ChatGPT
Yeah, it
moment
was used for all
happened.
the kinds of things you guys are kind of looking for. Yeah,
Yeah.
like chemicals
Yeah,
and
exactly.
and
Yeah.
hard science.
Yeah.
Okay, so I have to assume Australia, Chicago make these two massive investments. In many ways, this is still like a beta kind of system. It looked like these buildings don't get frozen in time. I mean, as you
Yeah, that's
continue
right.
to improve your
That's
stuff, it looked like since it's rack based, I guess you take those out and put
That's the plan.
new ones in.
It's going to be more complicated than
Okay.
that. But the
It's
plan
just like
is
that.
basically we rip out the blades and put
Yeah.
in new blades. And
Okay.
that's an involved activity, of course. But yeah, like, I mean, seriously, to the point, one of the things that is exciting about quantum computing, in contrast with conventional computing, which is starting to run up against profound challenges on increased density, where, Moore's law is
Fading, yeah.
slowing at
Struggle.
the very least. People are resorting to crazy kind of things like turning on 3 Mile Island and whatever. That's basically heading towards a world where it's really boring. All you do is horizontal scaling. With quantum computing, hopefully we're not in that regime. Like the first machines are going to be very far from optimal in terms of density, in terms of error rate, in terms of power consumption. And so, yeah, we should expect to look back on those first generation machines and say, man, that thing was horrible. Like in the same way that we look back on mainframes today and say, wow, that looks so primitive. So I think that's something that we already see with some of the intermediate scale systems that we're building today, where there are big opportunities for increased density. And we immediately build something and realize, man, we could have made this quite a bit more efficient, quite a bit cheaper. So I'm looking forward to that iterative process beyond the first generation systems. Yeah.
But, and I'm not trying to be hyperbolic here, but like 2027 comes, we can solve all kinds of new stuff. Is it like, oh shit, we're getting brand new medicines right then and there? I know it doesn't work quite like that. Or is it we need 3-4 iterations of even the building scale machines themselves to kind of get where we're hoping to go?
So our expectation and plan is that the first generation machine is lucrative for good reason.
Okay.
i.e. it is solving genuinely valuable problems that you cannot solve any other way. It's a fault tolerant machine, and it's something that people are paying for in serious way for serious reasons. But it is definitely going to be limited in terms of the scale of problems that it can solve. And we already know of problems where we would definitely require a much larger machine, and we intend to build those machines over time. Yeah.
Okay. Sorry, I have to ask this question. Like on the encryption thing, I mean, everybody freaks out about this, and it's like, if you guys end encryption, this is a problem, and you're saying like, if the machine is sufficiently good and big, we will in fact end encryption. Yeah. So what happens next after that?
Yeah. So there's a parallel universe where the scale of machine that you need for code breaking for encryption is smaller than the scale of machine that you need for commercial applications in chemistry, material science, etc.
Okay.
So imagine we lived in that universe. I'd be forced to build a scary machine before I build a commercial machine.
Okay.
Fortunately, we don't live in that universe. We live in the universe where the scale of machines that you need to attack encryption is much larger than the scale of machine that you need for commercial applications in chemistry and material science, as far as we understand. And so this is good news because it means that there should be, whatever you believe about our timelines, there should be an economic early warning sign where essentially we are lucrative before we're dangerous, and that's healthy for everyone, I think.
That was reassuring, but not. I don't know if that was fully reassuring. I mean, so there are issues to be solved. I mean, it's kind of like the AI conundrum in some ways.
Yeah,
it's like,
yeah.
shit's gonna get weird. We'll see how this plays out.
It is like, I mean, it has the same cadence as the AI stuff, where
Yeah.
people can make money before they're doing anything actually frightening, and then the distinctions are that, first of all, I never find myself on I'm very grateful to never find myself on a stage defending the claim that I might kill all humans, which the AI
Yes,
people have to deal with.
just encryption. It's like we're not going to destroy the universe.
And then, also this is something where, with one or two quite exotic exceptions, it's very hard to believe that you build a machine that's capable of any kind of significant code breaking without everyone knowing about it. It's bloody expensive. It's a huge, great machine. People, it's not something that someone's just going to build in their backyard
I see,
and
okay.
suddenly start stealing your Bitcoin.
Yeah.
There are also like clock speed limitations that are pretty significant on these things. So if you start doing the arithmetic on a hypothetical, whatever, Gen 4 quantum computer that's designed for code breaking, like that system would let you crack, I don't know, keys per minute kind of thing. So you could do something significant, but it's not doing mass surveillance, reading everyone's emails, ingesting gigabytes of data, nothing like that.
I mean, China has made quantum one of their priorities, right? I mean, they see it as like a huge national security type thing. Do they have anywhere near the number of startups the U.S. has? Do they have anything approaching what PsiQuantum is trying to do? Where are they in the quantum race?
Yeah, so China has pursued a bunch of different approaches on quantum computing, like basically all the classics, like superconducting qubits, spin qubits, quantum dots, photons. Zhao Weipan, who leads the Chinese quantum computing effort, is a photonic quantum computing person by background.
Oh, okay.
And they do heaps of really high quality work. So you can find papers where they're doing stuff that is, I would say, in the same kind of ballpark as what you see from Google. Various of the stuff that we do, you can find quite similar work going on in China. And yeah, they're definitely treating it with the same kind of urgency that the US is, that the UK is, etc.
Yeah, because I mean, you were talking with encryption about somebody taking all your Bitcoin, which fair enough. But I mean, I guess people worry too. It's just, it's like, okay, well then some rival nation can just sort of unlock the keys to your financial system, your communication, your everything, right?
Yeah, I mean, I think that definitely is like lodged in people's brains, that idea. But I also think that the motivation of these nations is quite a bit broader than that. Like actually, if I were a casual observer, I would maybe be inclined to think that nations only care about quantum computing for code breaking reasons, and all of the stuff about climate and healthcare is just fluff. And that really isn't the case from my point of view. Like the enlightened nations, from what I've seen, see this as a tremendous opportunity and perhaps the final frontier for computing, the only remaining thing that we can reasonably think of beyond AI. And that's much broader than code breaking, and I really think that's why they're going after it.
Just undermining the global financial system probably doesn't benefit a lot of.
It's not very commercially useful. As I said, there are practical, technical reasons why it's not a mass surveillance technology. I mean, and you can see this in the way that they talk about it, like the way that nations talk about funding for quantum computing. Code breaking and cryptography is usually a sort of afterthought. And a conspiracy theorist would reasonably say that's all fluff and nonsense, and behind closed doors it's all different. That's actually not my experience. That's not what I've seen from people.
That's what she would say. That's what you would say. Okay, that was awesome.
Okay, one, if you have time or want to, it's the, like, do you have a specific question that is unanswerable?
That you, yeah, okay.
Technology?
I would just say too, we talked a lot about chips.
Yeah.
Following the pain, like where is the chip at today? Like you mentioned a little bit, like not everything is to just the spec, but maybe give it just like a overview of like where it currently sits.
With
like,
the
components all there.
the chipset, with the chipset, and
Yeah.
okay, okay.
Yeah.
Okay, so for you personally, is there some problem you think about that you're excited to see if the machine can solve?
Yeah, I mean, so the categories are basically calculating the structure of molecules, how those molecules react and interact with other systems, and then properties of materials, and often like crystals. So things like a room temperature superconductor, for instance, things like perovskites that are used in solar cells. So this is all about like microscopic properties of things, where currently when we run the classical simulation of that system, we get completely unsatisfying answers. My favorite example of this is LK99, and you remember the tremendous excitement about room temperature superconductors that happened. I guess that was
Who could forget? Yeah.
like 2 years ago, probably now.
Yeah.
So that's a beautiful example where some Korean researchers pop up out of nowhere and say, we found this dream material, a room temperature superconductor, which would change the world. And they have this floating rock and so on that in Twitter goes absolutely crazy.
Yeah.
And one of the things that happened after that announcement was that the guys at LBNL fired up the supercomputer there and ran what's called density functional theory, so a simplified model of the behavior of those materials, which is simplified enough to fit into our conventional supercomputers. Somebody who actually studied with my co-founder Terry, Sinead, did some of that work. And the simulation finishes and it says, yep, this looks like a room temperature superconductor. And so that researcher jumps on Twitter and says, mic drop, we're in business.
Yeah.
Like the computer says yes. And of course it turns out to not be a room temperature superconductor. Like that is
It's a wild week.
to me, yeah, when ups and downs and so on. Like that to me is a good illustration of the fact that there are profoundly important questions where our conventional computers are severely deficient at answering those questions, and where there are fundamental reasons why we should expect that deficiency to persist.
Yeah.
And so yeah, I think that those are the kind of problems that we want to answer. And then it's about going from that idea to something very, very concrete. Exactly what molecule, exactly what precision do we want to answer that question with, exactly how many logical qubits with what logical error rate do we need, get the code written, optimize the algorithm. That's the work that our algorithms team does in collaboration with partners from industry and academia and so on. Yeah.
Okay. Like one of the most massive bets you guys made was that you were gonna lean into traditional semiconductor making for all the kinds of reasons you could expect. We know how to do that very well and do it cost effectively on huge scale. A normal semiconductor is moving electrons through these channels, these tunnels on the chip, and you have to make single photons go through your own waveguides or pathways, and then you have to have things to detect the single photons, and you have to have a switch that can deal with all this stuff moving around very quickly, and then manipulate the photons. Where today, I mean, you figured this out, and today it actually happens at Global Foundries, right? Which is one of the world's biggest semiconductor makers, and they can already make the chips. Like this is happening today. You've got this dialed in.
Yeah. So we had the advantage that was by design that we're able to start from an established technology, integrated photonics, where that's a 25-year-old technology developed for telecom networking applications. At GTC this year, Jensen was talking about co-packaged optics.
Yeah.
So that's where a lot of the networking for conventional AI supercomputers, data centers, etc., is heading towards that kind of photonics approach. And that's why we can even begin to make these microscopic photonic components in a regular high volume fab. The catch is that we needed to make all of those components way better than anyone else could make them. And we also had to integrate new materials, the most exotic of which is a superconducting thin film for single photon detection. So that is, like stuffing science fiction technology into a commercial manufacturing environment, basically. And that was, 3 years of work plus by our team, hundreds of millions of dollars of investment to establish that manufacturing process. And you look at the wafer and it looks flat, but you got to remind yourself that's a 35-layer process with metals, superconductors, silicon, ultra-low loss silicon nitride, and just an extraordinarily complex three-dimensional object. And it's just been amazing to see the team grind away on establishing that manufacturing flow, doing all of the design work on all of those photonic components, getting all the materials integrated, doing heaps of high throughput tests. So we do about 500,000 measurements per month right now here in Palo Alto. We now have our Omega platform where we have all of the components that we need, detector, switch, source, waveguide, etc., integrated into that flow, and they are all performing beyond the state of the art for each of those components. And that's, of course, not a hero device, right? Like that's not some kind of one-off in a university clean room. That's being built in a 300,000 square foot fab where they do 10,000 wafer starts a day and are making enormous amounts of silicon. And so that comes with a promise that we can essentially make as many of those chips as we could ever dream of. Yeah.
In America, no less.
In America, yeah.
Cool. I think we're good. We have to be good.
Let's get room tone.
Oh, room tone.